Today, we're going to talk about four equations that, honestly, are less like dry mathematics and more like poetry. They tell this incredible story of unification, of how two forces in the universe that seem totally separate are actually just two sides of the same beautiful coin. So let's just dive right in and see how deep these things run in our world.
So think about this for a second. What's the link between the Wi-Fi signal bringing this to you right now, the sunlight coming through your window, and the music playing on your car radio? I mean, they feel like completely different things, right? On totally different scales.
And yet, they are all explained perfectly by just four surprisingly simple and elegant equations. This is the story of how we, as a species, figured out the language of light itself. Look, to say these equations are important is a massive, massive understatement. They're not just important, they are the literal bedrock of our entire modern technological world. This isn't just some random list of tech. It's a map of electromagnetism working at every conceivable scale. You've got power generation and electric motors. That's the big macro-scale muscle of the equations. Then you have radio, radar, Wi-Fi. That's their voice, right? Carrying information invisibly through the air. And things like optics and MRIs, that's the equations working with unbelievable precision. They really, truly are running our world.
So, how did we get here? To really get how huge this breakthrough was, you gotta understand what the world looked like before Maxwell. It was a world of disconnected forces, basically a huge scientific puzzle just waiting for someone to put the pieces together.
Back in the early 1800s, electricity and magnetism were treated like two different subjects. You had your electric charges and currents over here, and then these weird, mysterious magnetic rocks over there. But then, scientists like Oersted and Faraday started finding these incredible connections. An electric current could actually create a magnetic field, and a changing magnetic field could create an electric current. So they knew they were linked, but nobody had the complete picture. The full story just wasn't there yet.
And this is where our hero, the Scottish physicist James Clerk Maxwell, steps onto the stage. Now, he didn't invent all the pieces from scratch, but he was the master architect. He was the one who saw how they all fit together into this one stunningly complete building. So, let's walk through his four big ideas, conceptually. No heavy math, I promise.
Okay, the first big idea, Gauss's law for electricity, is pretty intuitive. It just says that electric fields come from electric charges. Think of it like this. They flow outward from a positive charge and flow inward toward negative charge. More charge, stronger field. Simple enough, right?
Now, the second idea is kind of the partner to the first one, but it's got this crucial, fascinating twist. Gauss's law for magnetism says there is no such thing as a magnetic charge. You can't have a north pole without a south pole attached. They always come in pairs.
And this leads to a really key difference in how these fields behave. Electric fields can start on a positive charge and end on a negative one. But magnetic fields? They have to form continuous, unbroken loops. They have no start and they have no end. It's this fundamental asymmetry in nature, and it all boils down to that one weird fact: no magnetic monopoles.
The third idea comes from the brilliant Michael Faraday, and this is where things really start to get interesting and dynamic. Faraday's law of induction says that if you change a magnetic field, say by moving a magnet, you will create a swirling electric field. And this isn't just some neat party trick. It's the very principle that makes electric generators work. It's why we have a power grid. A changing magnet creates electricity.
All right, the fourth law. Originally, Ampere's law said that an electric current creates a magnetic field. Simple. But Maxwell added a game-changing new piece to it. He realized that a changing electric field also creates a magnetic field. This tiny little addition, this little piece of insight, was the key that unlocked the entire thing.
Because as soon as Maxwell added that final piece to the puzzle, something absolutely extraordinary happened. The four equations suddenly started talking to each other, and they revealed a secret about the universe that literally nobody saw coming.
Here's where the magic is. The equations create this perfect feedback loop. Get this. Faraday's law says a changing magnetic field makes an electric field. But then, Maxwell's new bit says that this new changing electric field has to create a new magnetic field in return. One creates the other, which creates the first one, back and forth, on and on, forever.
They just feed each other in this beautiful, perpetual dance. They create a ripple of electricity and magnetism that can keep itself going and travel through the total vacuum of space. It doesn't need any wires, doesn't need any air. This self-sustaining thing is an electromagnetic wave.
So Maxwell saw this popping out of his math, and he asked the most logical next question. His equations had these two constants in them, numbers that measured the strength of electricity and magnetism, which were known from lab experiments. So he realized he could actually calculate the speed of this new theoretical wave.
So he plugged in the numbers, crunched the math, and this is what came out. Almost 300 million meters per second. Now, for a physicist in the 1860s, that number wasn't just some random speed. It was eerily familiar.
And there it is, the punchline of 19th century physics. The speed he calculated for his theoretical electromagnetic wave was identical to the measured speed of light. The conclusion was just inescapable. Light isn't like an electromagnetic wave. Light is an electromagnetic wave. In that moment, Maxwell unified electricity, magnetism, and all of optics into one single magnificent theory.
So here they are in all their mathematical glory. And hey, don't let the symbols intimidate you. You don't need to be a physicist to get the big picture. Just think of it like this. The first line tells you where electric fields come from. The second line tells you that magnetic fields don't have a source like that. And those last two lines, that's the dance. That's the part that says how a change in one field creates the other. It's the entire universe of light, radio, and energy, all described right there.
But the story doesn't end there. Not even close. Maxwell's work was so perfect, so incredibly successful, that it actually became the launching pad for the next great revolutions in physics. His work is the absolute bedrock. For anything involving electricity and magnetism on our human scale, it's basically perfect. For the world of the very, very fast, it gave a young Albert Einstein his starting point. And for the strange world of the very, very small, it's the classical blueprint for our best theory of reality, quantum electrodynamics.
Just let this sink in for a minute. Maxwell's equations predicted that the speed of light is a constant. It's always the same, no matter how fast you're moving. Well, that one idea completely broke the old physics of Newton. It created a paradox that drove a young patent clerk named Albert Einstein nuts, and in solving it, he was forced to completely throw out our old ideas of space and time and invent his theory of special relativity.
Which really just leaves us with this one final, kind of mind-bending thought. For decades, Maxwell's equations were seen as a perfect, complete theory of reality. We now know they're what we call a classical limit of an even deeper, stranger quantum theory. So it just makes you wonder, what other ideas that seem totally separate to us today are just waiting for the next Maxwell to come along and write the poetry that finally unifies them?